Okay, we will start now. So first, uh, the first speaker present today is I will a little bit introduce to everyone. He is Chánh Tín. He was born in Huế, Vietnam, and Chánh Tín received the bachelor degree in electrical engineering from Da Nang University of Technology in 2015. And now he pursuing a PhD degree in electrical engineering at School of Electrical Engineering, University of Ulsan, South Korea. His research interests include the wireless power transfer, capacitive wireless power transfer, and resonant converters. So, welcome Tin to our webinar, and now it's your turn to present the topic. Thank you.
Thank you, Dr. Nam, for introducing me. First of all, I would like to share my screen. Can everyone see my screen?
Yeah.
Yeah. Okay. Okay. First of all, thank you, Vifex, for having me. And today I would like to present a topic with the title is Novel Bus Mode Control Strategy for minimum backflow power and zero the switching of dual active brake converters with the light load condition. This outline of my presentation today. First, I will talk about some background of DB converter, the motivation. And later on, I will move on to basic operation of the DB converter. After that, I will discuss about the proposed burst mode control. And then the proposed burst mode control is verified by experiment. Finally, I will conclude my presentation today. As you know that this is the system, most of the power electronic engineer know that we have a lot of system here like renewable energy and a battery for store the energy. Then we need to have the bidirectional power converter and also the wireless charger system for some EV. You can see here the
maybe the screen is not changed. It's still in slide 2, right? Or you change to slide 3?
No. Just
okay.
Okay. Yeah, do you see here the bidirectional converter? Then the application of bidirectional converter is they will have the power can float in bidirectional, and it is the very important in the system. And for today's topic, as you know that the dual active brake converter is very common for the bidirectional application, and the dual active brake converter with the, you can see here with both sides either with the full bridge, and the power can through to both direction.
Tí này hình như là khả năng em share lại màn hình hoặc là em mở full screen lên á, có nghĩa là cái slide của em nó vẫn đang nằm ở outline á, mà nó không thay đổi. Anh mới nhìn đây.
Ok.
Dạ.
Để em để em share lại ha. Ok. Để em share lại. Nó vẫn nằm ở giữa ha.
Được rồi.
Để share lại nè. Được chưa? Alo? Alo?
Thôi em chuyển thử slide xem được không? Tại vừa nãy anh thấy nó chỉ đứng im một slide à? Mặc dù anh thấy em nói đến slide tiếp theo rồi nhưng mà
Bây giờ anh cứ slide câu chuyện anh.
Màn hình chưa full anh ạ, màn hình vẫn đang bị nhỏ.
Màn hình chưa full rồi nè.
Dạ.
Có nghĩa là phải full mới ok. Rồi full rồi mình share mới ok. Vậy thì phải full trước rồi mình share sau. Ok, bây giờ stop share này, em share lại này. Phải full rồi mình share. Như vậy ok chưa?
Rồi ok đây không?
Phải là bấm full screen xong rồi share mới được. Không
Chắc là thế.
yeah,
Rồi ok đấy.
Okay, sorry for your inconvenience. I would like to continue my presentation. You know that the dual active brake converter has a lot of advantage, and nowadays a lot of research focus on how to improve performance of the dual active brake converter, and they have a main advantage so that you can achieve the zero the switching condition and wide voltage range and bidirectional power chamfer, and it have a symmetrical structure. But there's also some disadvantage of this topology in the line load condition, like non-zero the switching condition is and high backflow power. It leads to the low efficiency and high EMI noise. And you can see here, and this the voltage gain and the duty of the dual active brake converter. There's the boundary called the zero voltage switching boundary here, and you can see here this the active reactive brake reactive power, and in heavy load conditions you can see it's work very well with the in the zero voltage switching region. But in here you can see it line load condition, they will have a they will operate at the non-zero voltage switching region, and also the reactive power is very high, and that is some limit of the dual active brake converter. You can see this, and it leads to the efficiency of the line load condition is very low, and you can see with the loss of the system is contain two kind of loss, as you know, that the conduction loss and the switching loss, as well as the some fixed loss, so that the some gate driver power supply or any lot is just fixed. And in this presentation, I will present some control strategy to improve the line load condition. First of all, you can see in this figure, and in this strategy, they will it called burst mode control. It means that when the line load condition, they will turn off the every signal. You can see here it could turn on and turn off the system. It means that with this reason, there is no switching loss as well as conduction loss in the system, and it can improve the efficiency at the light load condition. You can see with the conventional system, they will have the load like this, very high switching loss at the light load condition, and in the proposed system, we use the burst mode control. The switching loss can reduce as well. The conducting loss can reduce, and the advantage of the proposed burst mode control is that we don't need any additional components, and we can achieve the load impedance zero the switching condition, and also we achieve the minimum backflow power. And in this presentation, I also introduce the DC bias current elimination. Okay, first of all, we will talk about the basic operation of the DB converter. You can see this waveform of the DB converter with the V primary is the AC voltage at the primary side, and V secondary is the AC voltage at the secondary side, and IL is the series inductor currents, and we can have the formula of the current, and we can also calculate the backflow power of this system. And there's the boundary of the zero switching condition here. And with this system, the optimal can be found with we can found the optimal by this equation, and we can have the minimum backflow optimal duty here. And with introducing the burst mode control, you can see here with the turn on and turn off with burst mode control, the voltage gain in burst mode can we can control the voltage gain by introducing the burst duty here. And you can see here, in case of the different burst duty, we can control the voltage gain, and we have we can use the burst mode dB to control the system. And after that, the voltage gain can be derived by this equation. You can see not only duty D, but also the burst mode duty. And in this case, you can easily to see that the output voltage can be regulated by either regulate duty D or burst mode duty. And we can also find the minimum backflow power of the burst mode, and we can have the update voltage gain of the burst here. And you can see in this formula, it means that the D is D optimal. It means that with this D, the system will operate at the minimum backflow power, and in this case, we can use the dB to control the M. That's it. It means that the system will operate at the minimum backflow power all the time with this formula. And also the zero switching condition of the burst mode is also very important. And but conventional system, they just introduce with some current reaction to achieve the zero switching condition. But in this paper, I introduce more about I consider the characteristic of the MOSFET. It's been the energy stored in the inductor should be greater than the energy lost in the system. And after that, we can have this a formula of the D, and we can have the new result is voltage gain for achieving zero switching condition for all load condition. Here you can see the conventional the gain here, and with the new gain we can have the new gain and new boundary here. You consider the price resistance. And also another thing is that the DC bias elimination, because we turn on and turn off the system frequently in the burst mode control. Then because we certainly turn on the system, there's always have some DC bias. But if the DC bias happened, you can see, because you know that the magnetic device, if the peak current is high, it makes the easy to saturate the magnetic component. In that case, we need to design some large margin in the magnetic design, and to then it make the more cost and more loss in the system. Then if we want to reduce that, we can introduce some another factor like DX here, and we can have the formula of the IA, IB, IC, and IAD here, and from this formula we can calculate the DC bias of this system, the DC here, and we can calculate how to eliminate this one to equal to 0. Then we can have the formula here, and after that we can have this D. It means that we can apply this D for at the beginning of the burst mode control. Then we can eliminate the DC bias of the system. And for designing the system, I also introduce some equation here to design system with the series inductor. We can have from the power formula and the zero switching condition formula, we can have the L should be designed in this range. And because this is burst mode, it will use in the some light load condition. It means there is some we should change to normal mode when we operate at the heavy load condition. And we can also calculate the critical value of the load resistance for the load change. You can see here we can calculate it, and the load change condition should be here. And also the output capacitance, we can use this formula to calculate it. And beyond the equation, we can have the formula, we can have the design procedure of the system from the initial value, like input voltage, output voltage, and output power, and switching frequency. Also, that we can choose the burst mode frequency. We can easily to calculate the series inductance and the burst voltage gain and optimal duty, and also critical resistance. And we can select output filter capacitor. And we also propose the algorithm that can make the load change condition when using the proposed algorithm. And from at the beginning, they will determine the load condition by measuring the output current. Then we can determine that which mode we should use. For example, if light load condition, we need to use the burst mode condition, but most, and if it's heavy load condition, we just use normal control. And for verified analysis, we use the experiment. You can see this DB converter, and this is some power supply and some power analyzer to measure the system efficiency. And this is some system parameter according to the design procedure. And first of all, is the DC bias elimination. You can see from figure A, the conventional system. You can see there is some bias at the beginning. We turn on and off system here. There's DC bias here, but when we apply the formula I present before, we added some D. Then there's zero DC bias current. Though is for two conditions in the buck and push mode. Though it's verified that we can eliminate the DC bias current. And with the step change of the output, we also test this, and you can see here we change the output reference and from 90 to 120, and then you can see the optimal duty should be updated to for the bus mode control. Then this is the actual value, and this the reference value of the optimal duty, and we can control the output voltage even in case of the step change of the output voltage. And we can achieve the zero switching as well because we operate at the optimal duty. Then we can achieve the zero switching condition to minimize the switching loss. And we also test with the step change of the load. You can see the IR will change because due to the load change condition, and the VR can be controlled by the control algorithm with the burst mode. And for the mode change, you will see here, for the burst mode, you can see the system will turn on and turn off frequently here. And in case here with light load condition, and when the system change from the light load to heavy load, then the normal mode will be take control of system. Then we will also have very smooth transition from the burst mode to normal mode condition. We measure the efficiency of the system with different cases. You can see here we compare with the burst mode with the SPS modulation with different angle, and we can have the much better performance in terms of efficiency. And for the conclusion, in this presentation, I present the some burst mode control for DB converter, and by applying the control the minimum backflow power as well as to achieving zero switching under light load condition. And DC bias issue of the conventional burst mode is also mitigated in proposed method. And the efficiency of the whole load range condition he also improve and experiment he conduct to verify analysis. If you interested more in this topic, you can read more on this paper, and this have the more analysis and more result, and explanation is done here. Then yeah, thank you. That's all my presentation today.
Thank you for your interest topic. I think. Now we move to the discussion of this topic. So, if anyone had a question, so please turn on the mic and directly question to the speaker.
Can I ask?
Hello?
Yeah, welcome.
Okay.
Yeah. Thank you for your nice presentation. You proposed the brush mode control for light load efficiency improvement. Did you compare the proposed method with TPS? That means triple phase shift.
Yeah.
That's a common way of improving the light load efficiency in the DAB. How you can say about the comparison between your method and TPS method?
Yeah. Yeah. Thank you for your question. First of all, in this research, we mostly focus on some simplicity of the system, and if we introduce the TPS system, because you know that TPS system had the 3 variable, and it's made difficult in control. I think with this burst mode, we just apply for SPS, but with same procedure, we can easily to apply for TPS. There is you can see here, in case of the TPS system, you still using some switch here, right? Some switch, and you will turn on and turn off switch here. And anyway, in case of the light load condition, there is the current go through here. If you have very good some optimization for backflow power, then the loss can minimize. But easiest way is just turn it off and then just turn it on in some circuit. Then it can minimize the switching loss as well as the conduction loss in this system. I think if the TPS can, but in this research we didn't compare with the TPS. Yeah.
Thank you.
Yeah, thank you.
Excuse me. Sorry about the inconvenience, but the meeting is set up is wrongly set up about the time. So we the meeting will be end with for about 10 minutes. So if the meeting is end, so please join again, and we will continue. Okay.
Okay. Yeah.
Sorry about that. Okay, I have a question. So can you back to the slide about the DC bias?
DC
Bias, yeah.
DC bias. Okay. DC bias. Okay, here, right.
Okay. I see that your contribution of your research is eliminate the effect of DC bias and improve the efficiency in the line load. But my question is why? Why do you have to do that? Because in the line load, your converter is designed to working at the heavy load, and the loss the thermal is not a problem line load, right?
Yeah.
So why you have to care about the line load?
Yeah. Okay. Very good question. Okay. Yeah. During research, we also think that's question. As you know that nowadays a lot of standard require that the efficiency at the line load condition of the converter should be mixed some condition. For example, if you at the line load condition the efficiency cannot greater than some number, then like your power supply cannot have that sender, then it cannot sell in the market. Yeah, that some sender requires some line load efficiency test to meet some minimum value, but more the line load condition is very low, and that's the reason why they want to achieve the line load condition efficiency.
Okay, thank you so much. And the second question is, you use the burst mode to improve the efficiency and the DC bias and the DC bias. The DC bias you solved by I call that is anti-bias, because you compensate the duty cycle to make the current is symmetrical. But my question is, how can you calculate the optimize NDX, and how do you change from the burst mode to the normal mode with the chance? Do you consider any transient of that?
Yeah, you can see from here, from IAIP and ISC and ID, and we can calculate the DC bias of the system here. And to make this DC bias equal 0, then we can we introduce the duty here, and for make this equal 0, we can use this to substitute to here. Then we can make the DC bias 0, and this is the first question. And that question is about the transient. Yeah, here you can see the transient, and because the burst duty is from 1 to 0. You can see the duty, the definition of duty is from 0 to 1, and from this formula we can calculate that, and if the load condition at the heavy load condition is made that the burst duty cannot regulate the system, as is our regulation range. It means that we need to change to normal condition, normal, and this one is some control flow chart. We need to detect the current, and then we can determine which mode we can use for a system. Yes.
But I wanna ask you about the transient, and how can you ensure that the parameter which you calculate is the same as the experiment? Because when you calculate the duty to eliminate the bias, you have to use the transient current, EA, EB, EC, and it is this current is depend on your parameters, and your parameter is not true, or not true. Look, I want to ask about the accuracy of your parameter mismatch to
parameter mix.
Yep.
Okay. Yeah,
Oh,
yeah. Yeah, parameter mismatch. Yeah, that's the practical issue. Yeah, I agree that in case of the experiment, there's always some tolerance of the capacitor, inductor, some measurement issue. Yeah, that's the another issue. But we didn't consider it in this paper. Yeah.
okay, thank you. Thank you.
Yeah, thank you. Thank you.
Okay. Thank you. So I also very interested about on this topic. So I also have some question. It's not about it's just about how can the audience here can learn a little bit from you. So can you come back to slide 7?
Yeah.
Yeah. As I understand that in the paper you focus on minimum maximum power and also achieve the ZVS condition to improve the efficiency. So in here, do you provide the closed form solution for the, for example, the passive the closed form solution? Can you share what is the technique you can obtain the optimal phase shift here to satisfy both of the condition, minimum maximum power and ZVS condition here?
Yeah.
What is technique can you obtain the optimal?
Yes, the you can see here this is a conventional system. The optimal D can obtain by in case when the backflow power equals 0, we can set this equation equals 0, and you can obtain the D. It means the to minimum backflow power is mean this equals 0, and we can find the D here, the optimal here. That's can we obtain the optimal D. And for the zero voltage switching condition, in this paper I consider the parasitic capacitance of the MOSFET. This equation you can see detail in my paper. There's a cited for my another paper will have the very detail how this equation come, and you can see from this equation we can easily to calculate the L, the I here, from I here, and from the current here you can put back it in this formula, and to this formula, then you can have this formula. We can have this formula of the D, and to achieve the zero switching condition as well as minimum backflow power, the optimal D should be greater than equal to greater than this number. It means that you need to operate at very close to this number, but not lesser than this number, because if lesser than, then you will lose the zero voltage switching condition. Yeah, it means that this number is some boundary of the minimum backflow power as well as the zero voltage switching condition. If you operate too far, then yeah.
So as I understand that, so you have two conditions. For example, one is the minimum backflow power. You can obtain the optimal one, and another thing is they also use the ZVS condition, and they also obtain another condition for D, right? So
Yes.
now you combine both of them, right? And you
Yes, sir.
can see the range is satisfy both of the conditions, right?
Yeah, right. That's right.
Okay. So I just think it is just maybe the nearly optimal, right? Because but for example, can you come back to the equation slide 7? Because
Seven.
I yes, both of the equation for
Em thấy có một diễn biến giả có một người nghe đang giơ tay xin câu hỏi, xin đặt câu hỏi chỗ anh Đình. Có gì anh?
rồi nhìn này.
Cảm ơn anh.
Mời bạn Nguyễn Đức Dương đi, có câu hỏi.
Chào anh ạ. Thank you for your presentation. I want to ask about the duty DB. I'm understanding that you ask more variable DB to control the system. So how much frequency of the DB?
Tín em mở mic.
Alo.
Ok.
Em nghe được.
Okay. Để em share lại. Okay. The DB is the bus mode bus mode duty. The bus mode duty here, and your question is about the bus frequency, right?
Yes.
Right. The bus frequency, and then you can see here with the bus frequency, the PB here, it's a function of the you can see here there's the optimal duty we can obtain by the conventional system and last equation, and with the M we can obtain by some voltage gain, and the L we can design, and the N we use is for turn ratio of the transformer, and the B here can be obtained by using some C here, because if you use the large, you can see where's the let's see, if we use the large, there's a trade-off when you're choosing the bus frequency. And for example here, if you use the large frequency, it's with a small spheres here, then the control is very good, but it may have the higher switching loss. But in case we use the very small large region, then it's the D here, they will make much ripple in the output ripple, and you can use this equation to determine that's the maximum burst frequency to for the requirement of the system. We can use this equation. Yeah.
So the burst mode frequency, is it changed with the converter or fixed?
In this case, it is fixed with the system. Yeah.
So when the off time of the burst mode, burst frequency, so if the load change at that time, I think the output voltage drop will be dropped really much. Do you consider about that?
Yeah, in this case, yeah, that's in this case we consider the drop of the voltage here, and there's the output capacitor. Right? The output capacitor will charge and discharge to maintain the output voltage, and in this case we also consider in this formula with the, you can see the VR.
The one point is the drop voltage also depend on the load, but I didn't see any kind of load in this equation.
You can see that at the MB is there's the content of the load here. And in the calculation, we can see the formula of the M. There's the you can see the R here.
Yeah.
Yeah.
Yeah, MB.
Yeah.
MB equal okay. Thank you. What's your point?
Thank you.
Thank you very much.
Well, welcome, Professor Ding. Can you open your mic and have a question to the presenter? So, Professor Ding, are you here?
Oh,
Yes. Yeah.
Because you called me professor, so I thought you are asking other ones. Okay. Hi, everyone. My name is Ding from Hanoi University of Science Technology, Vietnam. Actually, I have some comments rather than questions to the speakers. Because this research topic is also my research years ago. Then I experienced those before. Then I expect something more advanced, more significant improvement than this. Then I have two comments or questions. The first one is this consider the dead time? And the second one is this consider open loop or closed loop? Because I thought from what I saw in the slides, it seems to be open loop rather than closed loop. So when you operate the converters, then the parameter change or parameter identical, then you cannot meet the anti-bias completely, right? That is my two comments. Do you have any response?
Yeah, sure. Thank you for your question. First of all, this research we didn't consider the dead time in the formula because if we introduce the dead time, every equation is too complex. Then it's make the equation is not easy to handle. But in this case, we just consider the dead time. And the second question is
that is the point, because the dead time, if you fix the dead time, then you can see that the dead time is how do I say? No, kind of the dead time. The commutation time depends on the load condition, right? Commutation time it is different from the dead time. Commutation time depends on the turn off current. When you operate at the high power condition, then you transit at high current, then the commutation time is very short. But in contrary, when you operate at low current, I mean low load, then the commutation time is longer. Usually, in order to achieve soft switching, then you may want larger dead time, right? Otherwise, you are facing with the recommutation or early turn off or near ZVS transition. That's why dead time play an important role in this research. But when I did this research in the past, I did not reflect the role of the dead time because, as you said, it is very complicated. do you have any plan to reflect the effect of dead time in the future? Do you?
Because it did that time mostly for the zero switching purpose, right? And if we can have the enough current to discharge the output capacitor, then we just need the short dead time, no need to have very large dead time, because in this paper we operate at the optimal duty. It means that we already consider the enough the current to discharge the output capacitor to achieve the zero condition with the fixed dead time. Then we can achieve the zero condition with the fixed dead time, and we don't need to have the very large dead time in this case. Yeah.
Okay, how about the other comment?
Yeah, but we in this system we operate with the closed loop system, and you can see here with some output measurement of the output current, then we can determine which modes we can use for the operation, and we can calculate we can determine which buck or boost mode, and also we can calculate optimal duty. Yeah.
The DC bias current elimination there seems to be open loop, right?
The DC bias current elimination, you can see the formula here, and if we have the optimal duty, then we can update it frequently. Then we can have if we have the voltage gain, again we can update it according to the load condition.
Yes, that is what I meant. You can see here dx equal to something depends on M and DOP.
Yeah.
Then M is the voltage gain ratio, right? Then it depends on how accuracy you can measure input and output voltages. But actually, the input and output voltages measurements have some tolerance, right?
Yeah.
And it can be like 1% or 0.5 something. That means dx has some, tolerance. Then how come if there is some tolerance, 1 or 2% in dx or the optimal, then how it affects to the n prime?
Yeah, that's another issue of it is a practical issue if in case some mismatch in measurement, or it's could be some good point to investigate more on that. Yeah, but in here we not consider much on some mismatch in the voltage gain or the optimal duty. Yeah.
That is a very good topic for the future research, because I encountered this problem in the past when I fine-tuning the algorithm for one converter. There is no problem, but when I adopt to 10 pieces, 10 units, then it took me a lot of time to fine-tuning each by each. There is no, how to say, no algorithm at that time for fine-tuning, so I have to do it manually. That's why the approach, one reviewer asked me if I can do it in the closed loop. It means automatically adjusting the OP or the N prime to make it really bias elimination. Okay, so I think that is a suggestion for you for the future research if you continue this topic.
Yes, thank you, Dr. Jin. Yeah.
So, thank you. That's all.
Yeah, thank you, Dr. for your comment. Yeah.
Oh, thank you, Professor Deng. Yeah, have very good comment. if we want to eliminate the mismatch here, I think we can use the closed loop system to eliminate or to compensate the mismatch here. Yeah. I think it is very good comment. Thank you. Yeah. So, any questions from the audience? Oh, I have a small question. As a optimal phase shift ratio you obtain here by setting the vacuum power equals 0, but as I understand that in order to obtain the ZBS condition, it should be have the reactive power. That means it has to have the vacuum power, right?
Right.
Correct. So,
yes, correct.
but in the case, you set the vacuum power equals 0 to obtain the phase shift ratio. So, and you also verify the ZBS condition here. So, it is conflict. Do you think?
First of all, zero here is zero DC bias, not like a.
No. I mean, you set up the vacuum power equals 0 to obtain to obtain the optimal D, right? But
yes, right.
in order to achieve the ZBS condition, the vacuum power should have a little bit, right?
Yes, right.
But in the case, you set E equals 0, so how can you guarantee the ZBS condition?
That's why I told that the D here is the new D is introduced the already consider with the conventional D. There's the no considering of the some plastic here. It means with optimal duty, the same with the zero discretion duty. But in here, the optimal duty and zero discretion condition duty is different. By I introducing some COSS of the MOSFET here. In that case, the equation of the optimal duty is modified by this equation. Yeah, we consider more. Not only not only that this one. Yeah.
Okay, thanks. Yeah. Any questions from audience? Okay, thank you very much for the presentation. So now we will move to another speaker. So thank you. Yeah.
Thank you, Dr. Thank you, everyone. I will stop my shares.